Welcome back to ECE 442-542. You're being greeted back from spring break with a due date on your homework. Homework assignment number 4 is due this evening. There are hints on D2L. Hopefully you've already discovered those. If you haven't, please look in the little submodule associated with homework number 4. There are extra lectures / videos available for the zero order hold equivalents. That's lectures 4.2 and 4.3. 4.2 is by hand, finding the G of Z. Is that a hand indicating 4.2a? You have a question, okay? I don't know if you heard that at home. The question was in an email that I sent out during spring break. What's up with that? But some people were actually reading their email over spring break. If you did read your email over spring break, I said we really hadn't gotten far enough for you to stress out about problem number 5 on homework assignment number 4. We will talk about that, pretty much derive it today. And it's not going to be graded on your homework. You don't have to do it if you don't want. If you want to try to solidify the steps that we worked through, which we won't go through all of them here tonight in class, but it will be something that you need to know for exam number 2, which is Wednesday. So in 2 days and 48 hours, you will need to know it. You don't have to be responsible for it on homework number 4. It's do it if you want. If you have time, it might be helpful to do. In one of the homework problems, I believe it says obtain the answer in the back of the book using MATLAB in the zero order hold equivalent, and you can use directly this continuous to discrete function in MATLAB as long as your system, continuous time system, is in state space form. I'm trying to show you, and this is maybe confusing, but that line below is in MATLAB would be executed before the C to D command. Before you execute the C to D command, you would need to define this object SYS, which is an object of a state space representation of in continuous time. You would need to determine what your sampling period is, capital T, which is probably given to you, but that's based on omega sub s is 2 pi over capital T. Some of you are starting to stress a little bit with this 30 times the fastest frequency. That's a rule of thumb, which means that it's not a hard and fast rule that you have to absolutely positively preserve or hold to, but it's something that gives us a guide to where do we or how do we pick capital T, or how do we define or determine our sampling frequency. And that now gives us something that we can quickly determine if we know that, if we know the fastest frequency in our analog system is 14, then we need to go 30 times that to find our sampling frequency for the discrete time system. If anybody is still remaining in a couple of hours, or not quite 2 hours, at 7 o'clock this evening, I will still be here. We may get kicked out. I don't know if somebody's going to want this room. I didn't reserve it. Shh. If they do, we'll figure out what we do at that point. But we may just have to perform a hike. Maybe you have a bike, you can go. But if you're at home, you can just sit back and relax, go get and watch the next video, which will be the exam number 2 review session immediately following tonight's class. Exam number 2, again, is Wednesday, and the material for that we will talk about. And there are different transform tables. We've had one for exam number 1. I've given you a second one in terms of z to the minus 1 operators, or polynomials written in terms of powers of z to the minus 1, because we've used both Now you should be comfortable using either, and I think I'm allowing you to bring both to exam number 2. What we want to talk about today then is the process for exam number 2. We will try to summarize these discrete equivalents. Maybe the wording is misleading when it says equivalent. They're not exactly the same. They are simply discrete equivalents of a transformed expression, a system or a controller or a filter, and depending on which discrete equivalent you use, you'll get different resulting answers, but they'll be close. We'll talk about that via a table for the numerical integration strategies. Then we will get into problem number 5. I know you're anxious to get into problem number 5 on the homework, and we'll look at the forward rule for state space and then the follow-on. And I think in the email, if you read it closely over spring break, I said the forward rule is more straightforward than the backward rule to derive. And I'm just curious, show of hands, how many actually derive the forward rule? All right, I'm going back. I'm going to take my toys and go home. No one participated. No, I probably didn't expect you to do that, but I just mentioned it if you were interested. Then I'll give you a table, and that you should bring to the exam. If I ask you to come up with a state space representation for a numerical integration discrete equivalent, you better be able to plug or use the formulas for the appropriate discrete equivalent, whether that's forward, backward, or trapezoidal. We'll look at the pole zero mapping in a little bit more detail and talk about these zeros at infinity. That seems to be confusing some people, but it's really based on, and I think I've given you additional or background information on that, the number of z plus 1 factors in the numerator of your discrete equivalent really depends on your implementation issues or whether or not you actually want to or have access to the present value of the input into that filter or into that controller. Hopefully that will become a little bit more clear after the discussion tonight. But the zeros at infinity, those are fixed or determined by the transfer function in the S-plane. We find out the number of zeros at infinity from the S-domain description of our system, and then how we use that information depends on us. What I want you to go home with or to leave the semester with is, oh, you don't always have to have this many zeros at infinity. And in fact, MATLAB always uses one less than what we use. And so if you're comparing your answer to MATLAB and you're going, wait a minute, why do they just have one z plus 1 factor and I have 2? Well, that's just the way that they've defined or set up their discrete equivalent for pole zero mapping or matching. Process is consistent with the exam number 1 process. You get one more sheet of notes, front and back. But now you can actually bring both z-transform tables. The exam number 2 has a column for Laplace. It has a column for z. And those tables actually only contain transform pairs for causal waveforms. You have to remember, if we have anti-causal, there's a sign reversal when we go from time domain to frequency domain. If you have an anti-causal, you need to make sure that when you're going back and forth that you flip the sign in the transition from frequency to time or time to frequency. You can have a calculator, something to write with. You can't have this laundry list of no's. No talking or looking around. I know that's going to be difficult because there's going to be so many new faces in the room on Wednesday that maybe you've never seen well, depending on where they sat on the first exam, but I'll be looking at all of you and making sure that you're all in the right location. Calculator sharing, no, that's a no-no. Textbook, course notes, computer, cell phone, those are all unavailable to you during the exam. You can have at it after the exam. Yes? If you want to bring in extra sheets of blank paper, if that provides you with some comfort, you can. I usually try to bring some. If you don't have your own, raise your hand and I'll try to provide you with an extra sheet of scratch paper if you get a little bit long-winded in your answer, which is fine. I write bigger than others. Let's now talk. We're done with the announcements. We're done with where we want to go. Now we're going. Discrete equivalence for numerical integration strategies. That's when we convert directly this transfer function, h of s, in the s domain directly into the z domain. There's no hold device preceding the transfer function h of s. There's no zero order hold, which is what we use. You could have a first order hold, but we're just going to stick with zero order holds. That's not here when we're doing these discrete equivalents with the numerical integration strategies. If we're doing these numerical integration strategies, we're really replacing the variable s with some z domain expression. It's not a direct z plugging in for s. We have these different expressions. This table shouldn't surprise anybody, and it should be very familiar. We have the forward rule, which we've derived. We replace s with that expression, z minus 1 over t. Backward, we have an extra z downstairs, and then the trapezoidal is this bilinear, or this ratio of linear factors in the numerator and denominator, and that's what we now shove in for anywhere we see an s in our transform expression in the frequency domain to obtain the trapezoidal discrete equivalent. Now we're ready to begin the lead up to problem number 5 on homework set number 4. And that's doing these discrete equivalents using numerical integration strategies when our system is represented in a state space form. In the previous, we were assuming that we had some transfer function expression, capital H of S. Now we're assuming that this system that we're trying to convert from the continuous time setting to the discrete time setting is now modeled in a state space representation. And you might be confused with my inputs and outputs. That's why I've tried to explicitly label these. And you could think of this system being a controller, where the input to that controller is the air signal, that's the E, and the output of that controller is the input to the system, which is the output of our discrete equivalent. Hopefully that didn't confuse you, but the input is E, the output is U in this representation or in this description. And what we want to do now is convert that, go to the right, and try to find a phi, a gamma, an H, and a J. And the phi, the gamma, the H, and the J should be dimensionally consistent with the continuous time representation, and they should involve functions of A, B, C, D, and our sample period, capital T. This is really a picture of what we're trying to do. The system is right above us in state space form. And the input is E, the output is U, and now we want to find phi, gamma, H, and J. Here I've simply said phi, but that's now a function of the A, B, C, D and the sample period, capital T. That's our goal. We want to find these matrices in the discrete equivalent for our state space representation in the numerical integration strategies. Step one is what I'm assuming we can all do, and that's take the Laplace transform of that system of equations, that state space representation that we had in the continuous time setting. And since we're really just worrying about the dynamical behavior, not any solution, we don't need to worry about the initial conditions when we're performing these Laplace transforms. What that means is the derivative of little x of t, taking that into the S domain, simply says multiply that Laplace transform of little x of t by s. Multiplication by s in the frequency domain is consistent with differentiation in the time domain. We've now moved into the frequency domain, and if you're paying attention, if it's clear, I've tried to capitalize all of those variables. We now have capital X of S, we're now in the frequency domain. We have our state vectors Laplace transform, capital X of S. We have the Laplace transform of our input, which is capital E of S, and we have the Laplace transform of our output, U of S. The last equation is really just our output equation, and that's not dynamic in nature, and now we can simply capitalize those time domain variables that were in that linear equation or that static equation, giving us our output relationship in the state space representation. Now we can, or now I will probably slow down a little bit. Now we want to do step number 2, and that's replace S with the appropriate Z domain expression. And that's going to depend on whether we're doing the forward, the backward, or the trapezoidal. Homework problem number 5 had us doing the backward. Let's start with the one that I tried to tease you into doing over spring break, but apparently the tease wasn't successful. No one even batted an eye over that possibility. So now the S we are replacing with z minus 1 over t. And that S only appeared in one location. It's not going to be in the argument of all of these. It's just where we see an S floating around or scaling any of these variables or constants in the state space representation. That z minus 1 now goes out in front of capital X of z. We're now in the z domain, so now we switch the arguments of the x and the e, and this is now our dynamic relationship in the z domain in a state space representation. That, hopefully everybody's comfortable with that first step in step 2, just replacing or substituting for S the forward rule relationship, z minus 1 over capital T. Now we can continue. Let's clean this up a little bit. Let's get rid of that fraction. Let's multiply everything by the sampling period, capital T, and now we have z minus 1 times capital X of z equaling at x of z plus bt e of z. And what you need to keep clear is capital T is a scalar, A and B are matrices. But capital T is a scalar even though it looks like the same thing as A in terms of a capital letter. But A is a matrix, little n by little n. B is n tall by however many inputs we have in the E vector. Let's now isolate or put all of the z's that are scaling expressions on the left-hand side. And there's only one such term. We have z times capital X of z. And then we have 1 times x of z. That's this guy coming over from the left side of the equality sign plus AT times x of z plus BT times E of z. In general, A is going to be bigger than a scalar. It's going to be some matrix, so that 1 we are actually going to grow and just make it the identity. That little 1 scalar could be replaced with the identity matrix. The identity matrix being dimensionally the same size as the A matrix before. Meaning, I can now, if I wanted to have x of z plus AT times x of z, I could also write that in exactly that same way. If I multiply that out, distribute the x vector across those two terms, I get exactly what I had above, x of z plus AT x of z plus BT E of z. And now what I want to do is leave the frequency domain and go back into the time domain. And what happens when I leave the frequency domain and go back into the time domain with the expression on the left? Z times capital X of z. What does that look like in the time domain? What's the z as an operator doing to the state vector x in this particular term? It's advancing it by 1 sample period. What we now have on the left is little x at time n plus 1. And implicit to that is the sample period. If you really needed to know what actual time is, you would say, oh, this is at time little x, little n plus 1 times the number of sample periods. But typically we just don't even include the capital T in the argument. We just say, oh, we're at sample n plus 1. Our system matrix is the I plus AT. Capital X of n becomes little x of n plus BT E of n. And now we can say that here is in fact our system matrix in the discrete equivalent. There is our phi. That's the functional form of A, B, C, D, and capital T. It's not very involved. Here is our input matrix, gamma. And what happens when we take the output expression here, which we didn't even write down, did we, in the frequency domain? But do you see that we could immediately go into the z domain? We just change the arguments and then take that into the time domain in the discrete time setting, and we have exactly the same linear relationship between u, the state x, and the input e. That's now our output equation. Our output equation in discrete time says that we now have u of n is equal to c x of n plus d e of n. And relating those to how we define them in the discrete equivalent, we said, oh, let's call this a matrix H, and let's call this a matrix J. That's now our discrete equivalent. We now could say phi is I plus AT. That wouldn't be that hard to compute once you know the system matrix A in the continuous time setting, and capital T. How could you find capital T? I should see a bunch of thumbs up in the air. That's our rule of thumb, isn't it? 30 omega sub n. You would find the highest frequency in the A matrix, find the eigenvalues of the A matrix, and find which one is furthest away from the origin, and find that distance. That's your natural frequency that you would use. That's omega sub n. And you would say, oh, I need to go 30 times that. The input matrix, we simply scale the continuous time input matrix with the sample period, capital T. The output matrix is identical in both representations, as is the direct feed-through term. This is now the forward numerical integration discrete equivalent state space representation. And I really thought some of you would surely want to be talking about that over spring break. Forward numerical integration, discrete equivalent in the state space representation. You surely wanted to banter that around over spring break a little bit, once or twice, but apparently not with my T's in the email. That's the forward rule, and that is fairly straightforward, is it not? Now let's go into the next one. Now I've set this one up to fail, haven't I, since I said it's not as straightforward, but this is now 2B. This is step 2 with the second discrete equivalent numerical integration strategy, which is the backward rule substitution. And now we want to move into the Z domain via what substitution? Now we simply have to go back a page or two and find out what we replace S with for the backward rule, and that's now Z minus 1 over TZ being plugged in everywhere we find an S. And we've already found the Laplace of our continuous time state space representation. We now have Z minus 1 over TZ times capital X of Z equaling A X of Z plus B E of Z. All we've done now is replace what was in parentheses S with Z minus 1 over TZ. What's our strategy now? Probably clean up the fraction. So now, instead of multiplying everything by T, now we multiply it by something a little more interesting, T times Z, the advance operator in the time domain. Let's do that. Now we have Z minus 1 times capital X of Z equaling ATZ X of Z plus BTZ E of Z. Let's now combine the terms that involve Z on the left with X, meaning I have I minus AT Z capital X of Z. Is it clear where those came from? This came from that Z because I've slid the Z out of that, and the minus AT is I've moved this term over from the right side to the left side. I've subtracted ATZ times x of z from both. Now I want to put that minus x of z on the left on the right of the equal sign. I add capital X of z to both sides. That's now coming from there. And I have plus BTZ E of z. If you don't like all of those arrows, erase them if they're confusing you. But now let's go back into the time domain. Those arrows are just to try to give you a feel for where those different pieces came from. And what I actually want to do is I want to put all of my advanced terms on the left of the equality sign. That means I need to bring that BTZ E of z over to the left of my equal sign, and it's going to now be an advanced form of my input signal E. What else is over on the left? I have little x of n plus 1 minus AT x of n plus 1 minus BT E of n plus 1. What's on the right? I don't know why I'm getting a kick out of drawing these arrows, but I am. So that's the three terms that I put on the left of the equality sign. How many more terms exist on the right side of that equality? Just one, and that's in the time domain. What is it? That's just little x at time n. Well, this sure looks different than what we're used to seeing. Now, usually on the left, we just want little x of n plus 1. Now we've got a mess over there. This is why you were supposed to do this over spring break when you were feeling a little bit better, a little more relaxed. But now that we're excited about the exam, what can we do? Well, we're going to perform a little magic. We're going to make some of this difficulty go away by simply saying, you know what, that's a mess on the left, so let me just create a new variable and call that new variable all that mess on the left. Meaning, let me just make this a new variable, and I'm going to call that new variable w. And I'm going to say that's w at time n plus 1. And w at time n plus 1 is equal to the state in the discrete time setting at the present time little n. What I now have is I now have w of n plus 1 is equal to x of n. And we might want to keep track of that because we're going to use this later. So we'll call it star, and I'm thinking you guys are just really excited, so let's go, oh! That now is trying to clean up that mess that was on the left of the equality sign. What have we done? Well, let's just remind ourselves what we've done. We've defined a new variable to try to make our life a little bit easier. We've now said omega at time n plus 1 is this mess on the left. That's now x at time n plus 1 minus ATX at n plus 1 minus BT E of n. Or that's I minus AT x of n plus 1 minus bt e of n. Now, what do we want, or before we get there, if this is now omega of n plus 1, what can we now say omega of n equals? Oh my, I was so wrapped up in my derivation I didn't see all these hands going up. Yes, question, who's first? We lost a what? Thank you. They are just making sure that I'm awake, which I am not, apparently. I was getting ahead of myself. This is supposed to be, and I'm guessing if you were playing along at home, you'd already caught that in your notes. Uh-oh, another error? Question? Yes, so the W, I'm not even going to call it omega because somebody's going to say, is that a frequency, omega? Let me just call it W. My W looks like an omega, so put on whatever glasses you need to make that look like a W. But I'm just introducing a new variable to try to simplify our understanding or derivation of this relationship for our discrete equivalent. Let's not forget what we're trying to do. We're trying to come up with a discrete equivalent of a continuous time state space representation. And we're doing it based on a different numerical integration strategy, which is the backward numerical integration strategy, which, thinking it through, that's just looking back from the present time and approximating this curve, looking back from our present value of x. Now that I've corrected the right-hand side, if the top line is w at n plus 1, what's w at time n? Has exactly the same relationship, it's just one time step before. Meaning now w of n is I minus at x of n minus bt. Now I can use e of n. And what am I really wanting? If I'm wanting well, that's now an equation that contains w of n, x of n, and e of n. If I want a state space representation, I really want the input, e of n, and a vector, w, I'm running out of letters, x, v, y, whatever. We just want something at the next time step to equal a combination of what it was the last time step plus a combination of the error signal. This is now an equation right now containing w of n, x of n, and e of n. Well, we have w of n plus 1, but it contains an x at n plus 1 and an e of n plus 1. If we could replace that x of n plus 1 with a w of n and an e of n, then we would have a state space representation. So let's solve this expression for x of n. X of n is now, if we multiply on the left by the inverse of that matrix that's pre-multiplying x of n, we have an expression for x of n. X of n is now I minus at inverse w of n plus I minus AT inverse BT E of n. I've moved the minus BT to the other side, adding BT E of n to both sides, and then multiplying everything by the inverse of I minus AT. That now allows me an expression for little x at time n. And what did we have? Anybody have some candy, some now and laters? Is that even a candy? I thought it was. Anyway, we're at later. Now it's time to pull this back out. We now have w at time n plus 1, and we have an equation for x of n in terms of w at n and e at time n. Let's replace that little x of n with what we just found it to equal in terms of w of n and e of n. Here is now our later. That was the star, and that said that w of n plus 1 was equal to x of n, but now let's use that x of n there. Or we can now write that w of n plus 1 is equal to so this is now I minus AT inverse. We just had a little excitement in here. I don't know, that discrete equivalent has never been so exciting before, but now it's exciting. Sometimes you have things on silent and they still come on. Whew. Well, that won't happen Wednesday, will it? You guys will all be so focused. Maybe I'll have my phone do that and you guys can relax halfway during the exam. Where were we? Do you understand what I'm trying to do? Have I completely lost you? Now I have the right-hand side that I need for w of n plus 1. I need that right-hand side to only have w of n's and e of n's, and I have a way of replacing x of n with those w of n and e of n expressions. This is now I minus AT inverse BT E of n. And now this is my phi matrix. My gamma matrix is right there. What about my output equation? U of n is C x of n plus d e of n. But I have a way of replacing x of n with my vector in my state space representation, which is w of n and e of n. Or I now can say that this is equal to c times I minus AT inverse w of n plus I minus AT inverse BT E of n plus d E of n. You can now figure out what my H matrix is and what my J matrix is. J is the most involved expression. It's now I minus AT inverse BT plus D if you have a direct feed through matrix in the continuous time. Now you're number crunching and you're creating all these W's. Now you're going, well, I've got a W. I wanted to actually know what's my state, X, at various time samples. Well, we have a way of relating X to W. X at time n was just equal to W at n plus 1. If you need to know X, just compute W of n plus 1 and you have the state, the sampled version of the state. So if needed, X of n is now W of n plus 1. And that is what you can go home tonight and redo. Correct? That's now the backward substitution numerical integration strategy. Did I forget any arguments? I'm meaning n plus 1s and n's, etc. If not, let's look at the summary table. Oh, question. What was the question again? Repeat that. So now phi is the system matrix in this state space representation where our state vector is W. It's not the original state vector X. If we want to make that connection, then we can pull it out with that last equation that I wrote down. If you need to know what X is, you connect it with the W using that if needed sentence. But now in a state space representation you could say, oh, my system matrix is phi. And that's how you're evolving this W. But in fact that's how you're evolving the state X, because it's just one sample period behind in the WX relationship. So if that's making you uncomfortable, what phi is what? And to go back, now I would impress upon you that you can now go back and look at this forward and backward in the transform setting and see what you had for your discrete equivalence for a first order system, where your system might have been something at minus a, and see what that looks like for the forward and the backward. Where are your poles? In one case you were at I plus AT, where capital A could be a negative something. Here you have 1 over, essentially, because it's I minus AT inverse. They're consistent with what we've already derived in the transform setting in the transform expressions, and not the state space expressions. But the if needed is how you connect the original state vector with this new vector that we've defined, W. Let's now simply summarize that. And here the different matrices are advancing in rows. The phi now you can compare for the forward, the backward, and the trapezoidal. Aren't you glad I didn't assign you the trapezoidal? You're welcome. The trapezoidal is a little more involved, but it's kind of similar in derivation to the backward. The gamma, the input matrix, is now listed for the 3 different numerical integration approaches, and that's the square root of capital T that's floating around. Capital T is just a scalar. You can find the square root of that sample period. There's your H matrix, and there's your direct feed-through matrix J, as we derived for the forward and the backward. We didn't derive the third column. I'm going to leave that for you. But you now have that in your possession. Any questions on numerical integration, discrete equivalence? And these are scenario 1. This is when you do not have a zero order hold preceding your transform expression. The other way that we have talked about doing discrete equivalence in scenario number 1 involves pole zero mapping or pole zero matching. Let's go through that a little bit more, because we maybe went through it quickly before break. But now the idea is fairly straightforward. We take all of our poles in the continuous time transfer function h of z and map those to poles in h of s to poles in h of z. We map all the zeros of h of s to zeros of h of z, and those zeros involve finite zeros and infinite zeros. So number 2 contains quite a bit of information. And 3, we match the gains. And on the exam, I might say you decide how you match the gains. Somebody in office hours today was asking, how do we decide? Do we just pick? And I said, well, you decide what h of s looks like, and that's going to influence how you decide. If h looks low pass in behavior, then you want to match the gains at DC. If h of s looks high pass in nature, then you match the gains at high frequency. At high frequency, s is going to infinity, but what's z? Where is z going to? -1, and we'll try to help you better understand where that's coming from now. But the strategy is not too involved. 3 ideas, but it involves about 4 different steps, because row number 2 involves finite zeros and infinite zeros. And how many infinite zeros or zeros at infinity do you have, and how are those determined? S or Z? In the S domain or the Z domain? We now have 2 complex planes. Sort of the difference between this class and 441, 541. There we just had 1 S plane, complex plane. Now we're always playing with 2. We have an S plane, that's a complex plane. We have a Z plane, that's a complex plane. We need to figure out or feel comfortable going back and forth. What did I ask? Where do the zeros at infinity? Which plane are we dealing with to get the zeros at infinity? That's in the S plane. We play with h in the S domain to establish how many zeros we have at infinity. Then we determine how many of those we want to map to factors z plus 1. We might take all of those zeros at infinity to factors at z plus 1. MATLAB actually takes 1 fewer than the total that we're doing. And you could too, and there's reasons for doing that. And that's what I want you to understand after this discussion. Here's the approach. We're going to factor h of s into pole and zero factors. That will make it clean as to how we map poles and finite zeros into their appropriate factors in the discrete equivalent. Again, this is a discrete equivalent for scenario number 1, where we do not have a hold device. And that's one thing I hope you start to get comfortable with, is there's a ton of discrete equivalents that we've talked about. Zero order hold, that's scenario 2. Scenario 1 has even more. It has numerical integration, which has 3, and pole zero matching. Now we want to map poles. Now that we've identified the factors, pole factors and zero factors, we can map these pole factors of h of s to z-plane pole factors using this definition of z and s. Z is e to the st. Z is an advance by capital T units of time, or 1 sample period. That's the relationship. For example, suppose we start here. We have 1 pole factor. And where is that pole? Or what value of s causes that factor to vanish or to equal 0? That's when s is equal to minus a. If s is equal to minus a, then we can use this relationship to go from the s complex plane to the z complex plane. Or we now say that z is equal to e to the minus at. We've replaced s with minus a. Or we now have a factor like that in our discrete equivalent. I put the minus 1 because I'm not touching with the gain right now. But that's 1 over z minus e to the minus at. Yeah, but Dr. Tharp, what if you put a complex pole on the exam? You're just playing with real poles. Well, that's for you to figure out on the exam. Well, let's talk about it a little bit here. I'm teasing again. What happens if we have complex roots? Suppose now we have s is minus a plus and minus jb. Why do we have plus and minus? Because we're dealing with real coefficients in our denominator, and so we'll have complex poles appearing as complex conjugate pairs. If we just look at one of those through this relationship, z is equal to e to the st, let's look at the one with the positive j omega or jb. We now have minus a plus jb, that's s, times capital T. This we can now distribute that sample period across the two terms. We have e to the minus at and e to the j bt. That we can think of as r, and this piece we could think of as e to the j theta, where that might be theta d. That's our angle. So that if we now said, oh, z is equal to r e to the j theta, that's now r, and now we can use Euler, cosine theta plus j sine theta, to expand e to the j theta in rectangular form. We now have r cosine theta plus j r sine theta, or this is now the real part of our complex pole in the z-plane plus j imaginary component z sub I. And in fact, if we wanted to, once you've identified those poles in their real and imaginary component parts, we could rewrite that for the two. We had this one and its conjugate. Now we could write both of those together as a factor, z minus z sub r quantity squared plus z sub I quantity squared. And that's how you would map complex poles or zeros that are finite into the discrete equivalent using pole zero matching. That's the poles. You could do the same thing for the finite zeros. Let's write that down. So step 3 is map the finite zeros of h of s to z-plane zeros using the same connection of z and s. Z is equal to e to the st. as an example, suppose that our numerator was some k s plus b. What does that now look like in the discrete equivalent? Just that piece of our numerator, k s plus b. If we just were worried about that piece, how would we move that into a discrete equivalent? That would be the 0 location. The 0 as it is at e to the minus bt. The gains now might be a little different, so let's just say it's a k bar. And k bar is yet to be determined. We would match that depending on where we were at. Let's now spend a little bit more time on this notion of infinite zeros. So far in this class, we say infinite zeros of h of s. That's really just connected or related to the pole zero excess in h of s. How many more finite poles or poles do you have than finite zeros? And here I'm going to mix it up a little bit. Let me say that typically we've been mapping those to zeros at the point z equal to minus 1. To give us this factor z plus 1. Infinite zeros of h of s are typically mapped to zeros at the point z equal minus 1. Suppose we now had something like the following. Had s plus b, s plus f over s plus a, s plus c, s plus d, s plus e, s plus g. I'm just seeing if I know my alphabet. I skipped an f, but he was upstairs. Now, how many finite zeros? I just have 2 of those, and those are located at minus b and minus f. Number of infinite zeros. How many ways could you let s go to infinity and still cause h of s to vanish? How many factors could you allow that to happen through, or how many more poles do you have than finite zeros? You have 5 poles and 2 finite zeros. You have 3 zeros at infinity. So the number of infinite zeros is 3. And now that says that we would have z plus 1 cubed in our numerator factor in the discrete equivalent. Where the pole zero excess is the number of poles minus the number of finite zeros. What if I actually said I wanted to preserve a 0 at infinity in the discrete equivalent, meaning I wanted to have a pole zero excess of 1 in my discrete equivalent. How many of these z plus 1 factors would I have introduced in my numerator? If I want my pole zero excess in the discrete equivalent to be 1 in my h of z, how many z plus 1 factors do I want in the numerator of that h of z? Is my question clear? If I want a pole zero excess of 1 in the discrete equivalent, what's that saying? You want one more pole than you have finite zeros in your h of z. If I used z plus 1, 3 of those factors, I won't have any more finite zeros. I'm sorry, any fewer finite zeros than I have poles. If I now wanted a pole zero excess of 1 in my discrete equivalent, do you see that I would just introduce one z plus 1 squared factor in the numerator, not a z plus 1 cubed? And that will actually give me a 1 sample period delay between my input into the filter and the output. And that might be what we want. And that's what MATLAB actually uses. They use 1 fewer z plus 1 factors than they have pole zero or zeros at infinity in the h of s expression. And you might have seen that when you were comparing answers with your work using this z plus 1 power to the 3 in your discrete equivalent. Where's this z equal to minus 1 coming from, or why do we look at z equal to minus 1 as being consistent with a high frequency in the S domain? Suppose we looked at the S domain. Again, we have two different complex planes. We have the S plane and we have the Z plane. If I now said if I'm interested in the frequency response, and maybe I have a 0 here and I have a couple of poles here, and I'm interested in here's the real part of S and here's the imaginary part of S. How do I find the frequency response of H of S in the S domain? Where am I located, or where am I sort of active or paying attention to if I want the frequency response of a transfer function in the S plane? Where am I focusing my attention? To get started, where's DC? What's the lowest frequency in the S plane? Where would I evaluate H of S? At S equal to 0, and that would be right here. This is now DC. What if I wanted to say, oh, what's the frequency response at 1 radian per second? Where would I be in the complex S plane? If I wanted to know, how's my system behaving? What's its frequency response at 1 radian per second? I would be right here at J1. And I would evaluate all of these magnitudes and angles at that frequency. So I'm now looking at all of these points along the imaginary axis. I'm evaluating H of S when S is equal to J omega. I'm evaluating, that's how I get my frequency response in the S domain. What about in the Z domain? I said earlier that we now have to keep track of 2 planes, not Boeing or any of these are complex planes. Here's our Z plane. Here's the real part of z. Here's the imaginary part of z. And what's our relationship between s and z? That's e to the st. And what is s? Well, now if we're consistent with what we just said, we replace s with j omega. That's our frequency response, which in this case now says that z is equal to e to the j omega t. This is now our frequency response. Relationship in the z-plane. We evaluate z at e to the j omega t. Where does that put us in the z-plane? In the s-plane, it put us on the imaginary axis. Where do those locations map in the z-plane? Where does DC map? That's when omega is equal to 0. That maps to e to the 0, which is 1. Here's DC in the z-plane. What's e to the j omega? What's the magnitude of that? Use Euler and you see, oh, this is cosine omega t plus j sine omega t. Oh, you have cosine squared plus sine squared. That's always equal to 1. E to the j omega t always has a magnitude of 1. We're always on the unit circle for our frequency response. We now for our frequency response, we are now marching around not the imaginary axis in the z-plane. Now we're moving along. That's an ugly circle, but that's supposed to be a unit circle. A distance of 1 away from the origin. That's our frequency response. And what happens when we get over here to -1? Well, if we go any further, we actually are at a conjugate, so we really can't get any higher in frequency. Now we have a finite frequency since we've sampled. Before, we could go infinite in the s-plane, all the way up to infinity on that j omega axis. Now we can only go from 1 to -1. What do we know omega s is? Or maybe I should say, well, omega s is 2 pi over t. Yes, that's how we defined omega sub s, or that's how we find capital T. I now would like to say that the highest frequency that we can actually see in discrete time is based on that sampling frequency, and in fact, it's only half the sampling frequency. That's the highest frequency we have available to us in the sampled signal. What's that equal to? Omega sub s is 2 pi over capital T, and we're dividing that by 2. So our highest frequency is pi over T. That's omega sub h. What does that become? Well, if we now look at what do we end up with? We now have e to the j omega h t, but omega sub h is pi over t times t e to the j pi. What's e to the j pi? Using Euler again, that's cosine of pi, which is 0, plus j sine of pi. What's sine of pi? -1. So this is now -1. That now says our highest frequency right here, omega sub h, is pi over 2. pi over t, which is omega sub s over 2. So as high as we can go in frequency is from 0 up to pi over capital T when we sample, in terms of the frequencies that we can see. And that's another justification, hopefully, for why these high frequencies map to this z plus 1 factor. The z plus 1 factor corresponds to values of z equal to -1, and that's when we get over there at the highest frequency in the z-plane. That's why we're mapping these zeros at infinity in the S domain to factors of z plus 1. We may not want to map all of them. We may want to preserve some pole zero excess in the discrete equivalent, but we can play with that. That's where we will stop, and then we'll pick up somewhere after exam number 2, but obviously, you know, if you want, we can still have fun later this evening.